Hello, everyone. Welcome to our presentation about the firmware journey through the standards to the Arm SystemReady certification. We'll describe the new standard and its implementation in practice on the real life examples and the Marvell SoCs. So let me say a few words about the platform. So just recently, we had a collaboration on the Marvell Armada 7K and 8K SoC family, as well as its successor CN9130. So maybe a brief overview about the platforms and the SoC itself. It's a system on a chip from Marvell. It's dual or quad core Cortex A72 embedded controller. It has a significant amount of controllers, low and high speeds with 10G interfaces, PCI, SATA, USB, and so on. It was designed mainly for the both networking and edge application, as well as SOHO or enterprise that can utilize the crypto engines, network, and fast storage. Back in the day, 4 years ago, SolidRun, together with Marvell, created an accessible platform, Marvell and SolidRun Macchiato Bin. It's pretty known, and it's a general purpose board. After 4 years, I think it's still competitive. It has still competitive specs for most of applications, and it's maintained in upstream repositories. It was also one of the first ports of UEFI for Arm 64 in linear open platform package before it evolved to EDK2 platforms as we know it today. So a couple of years ago, Arm Server Ready standard was established with SBSA and SBPR specification that described how the hardware and the firmware should look like. It was meant for servers. However, there was an idea, why not certified on the embedded SoC, which was Armada 8040 and its platform Macchiato Bin dev board. So what was possible to achieve around 2018 and 19 was achieving SBSA level 1. It was the highest level that could be achieved, without real hardware, with the real hardware compatibility. UEFI with EDK2, TianoCore EDK2 firmware, ACPI 6.0, SMBIOS 3.2. Before the work was halted at the time, it was left in a state that it mostly passed the test suits, the tests from Arm Enterprise compliance suit. However, there were still a couple of outstanding SBBR, mostly SBBR tests that kept failing, but the efforts discontinued. In general, there was one can ask why it failed to get certified for the Arm Server Ready brand, and the answer is very easy. Just in overall, it's just not a server. It has something in common. It has generic ARM SoC and CPUs. It has PCI. However, it's not fully ECAM compliant. That was first issue, and it required quirks in the operating systems or firmware. In general, the ecosystem was not ready at the time. The ACPI support for embedded controllers was pretty poor. It's been evolving since then. However, most of the interfaces, embedded interfaces that are not non-discoverable via PCI bus, could not be used with ACPI, and although tried, the firmware could not work around all SBSA compliance issues, such as the version of the interrupt controller or the PMU interrupt numbers. So we achieved some compliance, some level of compatibility with the standards, but it was not pursued and sort of abandoned. So the support kept being maintained upstream. However, until recently, there was no kind of certification that could be used or help to standardize this kind of SoC until the SystemReady ES was defined. And it turned out to be the perfect match for Marvell SoCs. Fortunately, the previous work done in a couple of years ago paid off because of the work and getting used to and knowing all the way to test the hardware via test suits. That was very beneficial, and also all the queries implemented and to pass most of the tests could still be used, and we could just fix the outstanding issues. Just recently, 3 systems, thanks to these efforts of ARM and SemiHub, could have been certified. Macchiato been double shot, Solid Run CN9132 CX7 evaluation board, and Marvell CN9130 development board. They're now all upstream and ready to use for the customers that can play with compliant systems.
So ARM SystemReady program was introduced to extend and leverage and expand the success of the server ready, with a vision of having software just work across ARM devices from the cloud to the edge. The program was defined with multiple bands to accommodate the different combination of the standards and capabilities of these devices. The 2 bands that are important for our discussion here today are the ES, or embedded server, and the SR, the server band. You can think of SystemReady SR as the follow-on to server ready. So it still applies mostly to server, but platforms that follow the requirements and specifications of the servers could achieve that certification as well. So it's not exclusive only to server hardware. ES was designed to lower some of the hardware compliance requirements using a common base system architecture specification, while SR still requires the BSA, that common architecture specification, as well as the server extension with the SBSA. The interesting thing is that both ES and SR require SBBR and leverage the same standards, UEFI, ACPI, and SMBIOS, industry standards. With SystemReady ES, we are able to extend the success of server-ready for non-server hardware, especially on the IoT and edge segments, allowing those devices to fill in the gaps in the firmware, as long as the firmware is SBBR compliant and matches the requirements and passes the test suites, and with the common elements in the BSA hardware requirements. The silicon and devices built with that silicon can achieve certification, sometimes with waivers and with waiver levels that are defined and published by ARM that allow these devices to provide either workarounds or sometimes solutions in the firmware to hide some of the non-compliance issues in the silicon. This may be possible, like we found in several cases, with non-server devices that have limited PCIe topology, for instance, workarounds to hide some of the standard PCI access methods. So the question is then, well, how can a device get certified with SystemReady ES? Well, the process is simple. Partners, OEMs, silicon partners trying to certify the reference boards, ODMs, anyone that would like to certify a system first contacts ARM through the ARM SystemReady certification program portal on the web. We then work through with the partners to make sure that the hardware is available for evaluation, that the firmware is ready, and most of the development has been done on the firmware, whether it's open source or not. Once that the hardware and firmware is ready, then we start going through the certification phase, running the tests and discovering any gaps or issues that could be silicon or firmware issues, and then working with the partners through either bug fixes that are needed to meet those criteria and pass the tests, or waivers as necessary that need to be justified. Once the certification is complete and reviewed and approved, it gets published to the ARM SystemReady certification list, and this whole process is detailed in one of our specifications. The links are available in the presentation. The evaluation phase of the SystemReady ES certification focuses on compliance to the BSA and BBR specifications, so the hardware and the firmware requirements. We have a firmware readiness checklist. We do an initial run of the test suites and maybe some a quick test of OSs to make sure they work and make sure that hardware and firmware is available to run the tests. In some cases, we perform a gap analysis and work with partners to either help address some of those gaps or identify the development effort needed to address those gaps. The final stages of testing involve running the ARM architecture compliance test suites. Today, SystemReady ES systems are certified using the same test suite that is used for certification of server systems with the SR band, which is the ARM Enterprise ACS. The ARM Enterprise ACS has components that are open source. It uses the UEFI self-certification test, the firmware test suite, some SBSA specific tests that run in both UEFI and Linux, and the environment is packaged under an operating system from Linux with packaging called the Love OS, the Linux UEFI Validation OS. The latest release of the ARM Enterprise ACS is 3.0. We also have a new restructured SystemReady specific ACS test suite. We have a flavor specifically for the ES, and we have other flavors for IR as well. And that currently that test suite is in a beta release. It's available publicly and working towards a formal 1.0 release to replace testing with the Enterprise ACS.
So why this effort is even done? We get certified hardware, and for what reason? The main purpose of all the efforts is to ensure the platform and its firmware will just work with as wide range of the existing ecosystem as possible. And for this, when someone is certifying the platform, the OS should be tested as being able to get installed out of the box with unmodified firmware using the existing ISO images just downloaded from the web, as one is used to do for standard PC device. So now you can, in the screen, you can see examples of the OSs that got installed this way without any issue, just going through the menus, picking the storage and all relevant packages that can be installed, and they could be booted using even the graphical output, which of which photos you can just view. So here we have the CentOS 8 stream. Further, Debian 11, Fedora 34, Ubuntu 21.10, the development version of Ubuntu, the latest ones. OpenSUSE Tumbleweed. Now it's not an OS, but the hypervisor of VMware, the ESXi Arm Flink version 1.5. FreeBSD and OpenBSD current images. And last but not least, it's just very recent example of how generic firmware using standard interfaces can work with sort of a black box OS without any sources and any modifications. It's a fresh demo of Windows 11 working both in a VM and natively on a platform that has a standard certified firmware, but also the platform is not new. The ecosystem evolved to support such ARM64 devices, but also it's a great showcase of how existing device can meet the standards and fulfill any requirements that are need to be met just to boot the system out of the box.
Once the OSs are verified to just work and OS logs are collected and certification tests are completed and the tests pass, they get reviewed, the results get reviewed by ARM, evaluated. The waivers, like I mentioned earlier, needs to be approved by ARM, and it's case by case and needs to be justified with workarounds or fixes going upstream or future fixes that are in the pipeline. And eventually the certification gets issued by ARM, it gets issued to the partner, and the website where the certification list is hosted gets updated, showing the details of the specification, including the firmware that was used for the test and the operating systems that were tested for that specific certification. Now that we went through the certification process, let's cover some lessons learned and best practices that could be used in through your journey of system ready and standards compliance. The first point that we want to mention is it really starts with the pre-silicon. The specs exist, especially the BSA and the SBSA. They exist to help hardware designers and integrators, silicon providers, and their EDA partners to build ARM SoCs that have the compliant components and pieces of the hardware in order to fit in the overall story, gets enabled by the firmware and gets recognized by the OS in a generic way. So pre-silicon testing and validation, working with the EDA partners that have developed SBSA specific verification solutions, and doing a shift left on the testing early enough in the hardware design process is a very important lesson. Once the silicon is taped out, then there is just so much that can be done with firmware workarounds if there are some big silicon compliance issues. The second point we wanted to mention is leverage the open source and commonalities that SBBR is built on. SBBR is built on standards like UEFI, ACPI, SMBIOS, and Arm trusted firmware interfaces like the SMCCC and PSCI. There are open source projects and upstream communities around these, like the TianoCore and the TrustedFirmware.org. Having SystemReady does not require that your firmware is open source, but leveraging commonalities in these open source and upstreaming them when possible enables a better story of the firmware for devices that choose to do so. Of course, there is also commercial firmware solutions, and those are absolutely acceptable for SystemReady certification, and they are built upon the same concepts of leveraging modular and reusable code. One of the things we want to talk about quickly is PCI ECAM being a very common issue that we see in compliance in the system. Typically, that's not addressed to pre-silicon, so you end up with ARM SoCs that don't have a standard ECAM or have ECAM implementation but not completely standard. The solutions vary. Mostly, SystemReady ES allows firmware workarounds to either hide things from the OS or do some other tricks in the firmware so the OS can access the PCI devices in a standard way. The other options end up really being some quirks in the OS that require platform-specific knowledge to know how to decode the PCIe access. ARM also has published a standard specification to abstract the ECAM hardware through a firmware interface that if operating system supported and platform supported, then that could be a good way of working around the issue. The other issue I want to mention is the UART. That becomes very important for the console for the OS. The BSA standardizes either the ARM generic UART, such as the PL011 ARM IP, or a 16550 fully compliant UART. This is still a pain point today in the ecosystem, especially around embedded and IoT devices. It's easy to fix pre-silicon by just making a choice to pick an IP that offers a seamless OS just works solution.
Last but not least, a general advice for the OEMs and ODMs is to enable networking. Most of the embedded systems usually offer the embedded network interface controllers that in most cases don't have the ACPI supporting the OS. So it's a very good addition is to add standard USB to Ethernet or PCI Ethernet card just to offer smooth installation. And the last thing is the firmware accessibility. So the certified boards have everything open source and public in the upstream repositories, and also the binaries are publicly available for downloads and use by all the users. It's also make easier the future certifications for other boards based on the same SoCs. Thank you for attending our presentation, and we'll answer all the questions in the Q&A session.